How do you route high-speed signals in PCB design? Imagine trying to send a message across a busy city without any traffic rules or clear pathways. The message might arrive late or get lost entirely. In printed circuit board design, high-speed signals face a similar challenge. Ensuring they reach their destination intact requires careful planning and precise execution. High-speed signals are characterized by rapid changes in voltage or current, often in the range of hundreds of megahertz to several gigahertz. These signals are sensitive to interference, signal degradation, and timing issues. To maintain signal integrity, designers must adopt specific routing strategies that minimize these problems. One fundamental approach is to keep the signal paths as short and direct as possible. Longer routes introduce additional inductance and capacitance, which can distort the signal waveform. Shorter traces reduce the likelihood of electromagnetic interference and crosstalk between adjacent lines. When routing, it is also essential to avoid sharp bends or right angles. Instead, gentle curves or 45-degree angles help maintain consistent impedance and reduce signal reflections. Impedance control is critical for high-speed signals. Designers often specify a characteristic impedance for the transmission lines, typically around 50 ohms for single-ended signals and approximately 100 ohms for differential pairs. To achieve this, the width of the trace and the distance from the reference plane are carefully calculated based on the dielectric properties of the PCB material. Maintaining a consistent impedance along the entire length of the trace prevents reflections that can cause data errors. Differential signaling is another technique used to improve noise immunity. It involves routing pairs of traces that carry equal and opposite signals. These pairs are kept close together to ensure they experience similar interference, which cancels out common noise when processed at the receiver. Proper routing of differential pairs involves matching their lengths precisely to prevent timing skew, which can cause data corruption. Grounding and shielding are also vital. A solid ground plane beneath the high-speed traces provides a low-inductance return path, reducing electromagnetic interference. Sometimes, a dedicated ground trace or a guard trace is placed alongside high-speed lines to further isolate them from noisy signals. Additionally, placing ground vias strategically along the route can help maintain a stable reference and reduce electromagnetic emissions. Layer stacking is another consideration. High-speed signals are often routed on inner layers with continuous ground or power planes above and below. This configuration minimizes parasitic inductance and provides a controlled environment for the signals. When designing multi-layer PCBs, careful planning of the layer stack-up ensures that high-speed signals are routed on layers that optimize their integrity. In summary, routing high-speed signals in printed circuit board design involves minimizing trace length and bends, controlling impedance, matching differential pairs, providing solid grounding and shielding, and thoughtful layer stacking. These practices collectively help preserve signal quality, reduce electromagnetic interference, and ensure reliable high-speed data transmission across the circuit.